Hello everyone. So this is a recording to discuss the working of experiment number 3, that is specifically the experiment to write an assembly level program to find the number of zeros and ones in 32-bit data. So in this experiment we are basically going to look at what is the logic that is generally used for counting the number of zeros and ones in any given binary data stream, and how we are going to implement that logic. Let's look up a very simple algorithm that we're going to use, and how that algorithm we're going to implement using an ARM Cortex M3 assembly level program. So to start with, let's just first understand number systems and the algorithm in general. Taking a very simple example of any given number. Now I am taking a 4-digit number. So this is a number in the decimal number system. Now converting the same number into hexadecimal, where the base or the radix is 16, the number ends up as being 156E. And as we are already familiar with this, I'm not going to go into the depth, but uh, the hexadecimal number system can very clearly be written into a binary stream based on the hexadecimal equivalent. So 1, 5, 6, and E. So that becomes the entire binary representation for the decimal number 5486 to the base 10. Now, based on this binary representation, you can clearly count the number of ones and the number of zeros that are there in this binary representation. And the objective of this program is to count them. How many zeros are there? How many ones are there? So, in order to accomplish this job of counting, what we really do is we use what is called as a carry flag, and we are going to use a rotate operation along with the carry flag. So, since the ARM processor already has got this option of using an assembly level rotate uh, instruction, and there is also the option of checking if there is a value stored into the carry during the rotation operation. So we are going to use this feature to check that if a rotation happens, and during that rotation, if a 0 comes into the carry flag or if a 1 comes into the carry flag. Now, if a 1 is coming into the carry flag, then that is correspondingly has to be taken into count. That is, how many times a 1 turns up in the carry flag, that will have to be counted. And how many times you don't have a 1 in the carry flag, that is also counted. So the number of times a 1 is encountered, that count will be stored in one register, and the number of times a 0 is encountered, that will be stored in another register. And this is taken as the basic principle of working for the program that we are going to use. So quickly, if you are going to summarize the whole thing, we are going to take our binary number, do a logical rotate operation on this, and that logical rotate operation will take this binary number through the carry flag, and in the carry flag you are going to check if there is a carry or a not. So if there is a carry, then one register will count the number of times a carry is generated. If there is no carry, then that is also counted in another register. And the numbers that you finally get after the complete count is going to be the number of ones and number of zeros. To be more precise, in this case, we are taking a number which has got 4, 8, 12, and 16 bits in total. So in order to count the total number of ones and zeros into in this particular number, we are going to have to count, we are going to have to rotate this value into the carry flag 16 times. So after 16 complete rotations into the carry, we will be able to tell exactly how many zeros and how many ones are there in this number. So here we are taking a 16-bit number. In the similar way, in the program that we are going to execute, we are going to take a 32-bit number. So the number of rotations that you are going to have to do is going to be 32. So 32 rotations Each rotation goes into the carry flag, count the number of zeros, count the number of ones, and that should give you the answer in two registers. So to accomplish this, we are using a program. So this is the whole program that we are actually going to use. Let us look at this program into two different small simple parts. So the first part of the program, we have to initialize the program. That is, we define that this is a code region of the program. We define the entry point, and we are giving this program a name called as zeros and ones, so that this can be called from the C program that we are actually going to call as the main program for us. So as discussed previously, the same methodology we will use here also. And now, before we can continue, we are going to use four different registers in this case. So we have to load these four registers with the values that you need. So the first register we are going to use is R0, and R0 is the register where we are storing the data value that we want to actually check in the program. So in this case, I took an example of 156E. You can put 156E here, or you can put a number of your choice. So right now I have loaded the number 1, F, A and 3. So why don't you check what is the number of ones and zeros in this number by writing it on your own. Okay, moving forward, we have to actually talk about a number. In this case, we are talking about a 32-bit data. So if it is a 32-bit data, the number of rotations that you have to take is going to be 32. And 32 when converted into hexadecimal is nothing but hexa 20, 20. So hexa 20 is nothing but decimal 32. So we are going to load hexa 20 or decimal 32 into register R1. So this is the register which will keep count of the number of rotations. So the next registers that we are going to use are R3 and R4. R3 we will use for keeping count of the number of ones, and R4 we will use for keeping count of the number of zeros. So before we can continue with anything else, we are going to clear R3 and R4. They may have some unnecessary value in them, and we don't want to add into that value or subtract from that value and change any result that we are going to get. So we are going to clear R3 and R4 by loading immediate 0 into both of them. Okay, so this is the first part of the program. So what really we did was initialize the code, define a name for the function that will be called, and after that set one register R0 for storing the value that you want to count the ones and zeros with, set R1 with the value 32, decimal 32 or hexadecimal 20 for counting the number of shifts that have happened. Then we are going to clear R3 and R4 for storing the number of ones and storing the number of zeros in R3 and R4 respectively. So this was one half of the program. Now let's go to the second half of the program. In the second half of the program, first we have loaded the value already into R0. That value has to be shifted right. Shifted right. So if I am saying shifted right, then the LSB bit will be shifted into the carry flag. The LSB bit of your number, that is the last bit of your number, will be the number which goes into the carry flag. So if we have if you are looking at one flag here, which is called as your carry flag, then when we do a logical left shift, then this one will go into the carry flag, and eventually all of these will be shifted by one bit, and a 0 will be added into the MSP. So this is equivalent to what we are going to get as one logical shift right, LSR. So that is what we are using here, LSR. So R0 is LSR'd one times, and the result is again stored into R0. So in one cycle, one rotation happens. Now immediately after that rotation, we are going to do checking, or we are going to add if there is a carry. If the carry is set, CS is for carry set, add if carry is set, R3 with a value of 1 and store the result into R3. Add if a carry is set, R3 with a value of 1. Add if the carry is cleared, if there is no carry, then you add R4 with 1. So what we are basically doing is, if there is a carry, increment R3. If there is no carry, you increment R4. So immediately after the shift, check whether carry is there. If it is there, increase R3. If it is not there, increase R4. And finally, once both of them are done, we are going to decrement R1, because you should remember R1 has the number of shifts loaded, and we initially loaded it with 32. So this will be decremented by a value of 1. And once it decrements, R1's value will be compared with 0. That is, you are checking if R1 has reached 0. If it has reached 0, then it has to break this loop. If not, we are saying branch if not equal. BNE is for branch if not equal. If it is not equal, to 0, then this has to be looped back to label, and label will again take it through the same program. So this cycle will keep repeating until R1's value becomes 0. That is nothing but 32 times this entire cycle will happen. And during that entire 32 times, R3 and R4 will keep checking the value of carry after each logical shift. Right? So this is the entire program together. Initial part, you do an initialization. After that, you do a logical shift and check if there is a carry. If there is a carry, you increment register. If there is no carry, you increment another register. Keep count of the number of ones and zeros that you are encountering during the entire shifting operation. And once you have completed the entire shift, you stop. If not, you keep repeating. So this is the whole logic of the program that we are going to use. Now let's execute this program and see what is the result that we are supposed to expect here. So I have already written a C program for this. Let me open that. So this is the C program where we are calling in two different functions. The first function we are calling in is our main C program, into which we are going to call this main zeros and ones function, and into the second one we are calling the when the assembly level program is called in the main program again, then the C program will execute this assembly level program, and once the execution is completed, we are going to put the whole program into an infinite loop so that it stays here. So this is the standard C program that we are using for all our assembly level programs in the syllabi. So the same thing I'm using here again, but I am going to call this function which we have already named in our assembly level code. So since I have explained the whole thing, let's just go ahead and execute it. I'm going to first build this target. Okay. So once the target is built, don't forget you need to check if the build is complete, right? So if the build is complete, it will clearly tell you that errors are 0. Don't worry about the warnings. Just check if the errors are 0. Once you have the error 0, then you can go to the debug. So this is the debug, or the same thing is available here. So let me start the debug session. Now in the debug session, initially our registers are going to be 0. So to show you if the registers are going to be 0, I am going to put the breakpoint here. Okay, after the label I'm going to put the breakpoint, and let me do the execution. So when I ask it to do a run, it will come and stop at the breakpoint. So by now what all has happened, into R0 we have moved 1A F3, into R1 we have moved 20, and R3 and R4 have been cleared. So you can see R3 and R4, both of them have been cleared. So R1, R3, R4 R0. All four of them have been set for us. Now after this, as we repeat the cycle, we can see what left shift happens, and with each left shift, how this number is going to behave. So the number that we are using right now is 0001 F. A would be 10 and 3. Right? So this is the binary equivalent of this number that we are using right now. Okay, so let's see what happens. I will execute this once so that this loop executes once, and after one cycle of the loop, what does really happen? So I'm going to run this. So now you can see it has run entirely once, and once it has completed the run, R0 is currently got the value FD1. That is, this entire thing has got shifted by one time. So now what we really have is 4 zeros followed by 4 ones, followed by 2 ones, 0 1, followed by triple 0, followed by what is this, triple 0 1. So that is basically F, D, and 1. So this is the number that you are actually looking at in the register right now after one logical right shift. Now, incidentally, what happened? Into the carry flag, we have loaded 1. This right shift has loaded 1 into the carry flag, right? So I think we will be able to see it. It is here, yeah. So the carry flag is loaded with 1, and with the carry flag loaded as 1, obviously what we are supposed to do is R3 will be incremented by a value of 1, whereas R4 is not incremented, it is kept at 0. So now next cycle, what is going to happen? Again a 1 is going to be pushed into this, right? So let me take the whole thing, and now what we are saying is we are adding and this one is going to be there in your carry flag. So this is the number that we are going to get in the next cycle. So this is what? 7E8, 07E8. So let me run this again. So you got 7E8 in the next cycle, and again a carry flag is generated, because of which again R3 will be incremented, R4 remains 0. But now during the next cycle, you can see that the LSB bit right now is 0. So during the next cycle, into the carry flag a 0 will be loaded, and because a 0 will be loaded, R3 will not increment. We don't want R3 to increment, but instead we want R4 to increment. So right now the value of R4 is 0, and that one will be incremented when we do the next cycle. So the value during now after this rotation is going to be 3F4. So let's see what happens. We get 3F4, and this time our carry flag has not yet been reset. It will get reset in the next cycle. So, but what really happens is the R4 value got incremented, R3 value remained 2. So this operation will happen, and we will have to do this entire thing nearly 32 times. So I am just going to remove this break and allow it to run for the entire duration now. So I'll give it a run, and now at the end of the run you can see that it is clearly telling you the R0 flag is completely shifted out. All the bits have become zeros now, and you can see that the values in R3 and R4 are giving you the results of 9 and 17. So that is what we initially started with here. So this is what we have written is here is a 16-bit number. If this is actually going to have a 32-bit number, that is the remaining 4 words are actually going to be zeros. So you are going to get that many number of zeros, or 16 zeros are already going to be there in the beginning, and in addition to that the number of zeros here. So let's just count the number of zeros. 16 initially, 17, 18, 19, 20, 21, 22, 23. So that is the number of zeros that you have. 23 in decimal, if you convert it into binary, so that should be the same thing. So 16 plus 7, yeah, 23. So that is the number of zeros that you have, which is represented in the R4 register. In the R3 register, we have the number of ones, which is nothing but 32 minus 23, giving you 9 ones. So the 9 ones and 23 zeros are counted in this manner using this program. So I hope you have more opportunity to explore any other techniques. This is one way of doing it, but not necessarily the only way. I would definitely encourage you to try more ways of doing the same program. And with that, I think we will wind up this explanation. Bye bye. Take care.